Imagine trying to hear a whisper from clear across the universe. That's basically the challenge for scientists who are hunting for gravitational waves, these teeny, tiny ripples in the fabric of space-time itself. And to detect them from space, you have to build an instrument on a cosmic scale. The biggest problem? Simply aiming the lasers. So here's the plan. You fly 3 spacecraft in a giant, absolutely perfect triangle. And these things are separated by millions of kilometers. This whole formation acts like one colossal detector. And it's so sensitive, it can feel the stretching and squeezing of space-time when something huge happens, like 2 black holes collide. Now, to measure these unbelievably small distortions, you have to connect the corners of this triangle with laser beams that are perfectly stable. They become the universe's most precise ruler. But as you can imagine, keeping that connection locked in is a massive, massive engineering challenge. Right? I mean, it is the ultimate long-distance shot. Even the tiniest bit of uncertainty about where a spacecraft is creates a huge search area. Hitting that target is the fundamental problem we're going to dig into today. And believe me, the solution they came up with is incredibly clever. So this huge triangle of lasers, it has a name. It's called a laser interferometer. But really, you can just think of it as a ruler made of pure light, designed to measure changes in distance that are almost unimaginably small. And when I say small, I really, really mean it. We're talking about picometer scale precision. That's a trillionth of a meter. It is just a mind-boggling level of accuracy. And it's exactly why every single part of the system, especially pointing those lasers, has to be absolutely perfect. Okay, so this brings us right to the first major hurdle for a mission like this. You've got to find and lock onto the other spacecraft. It's what engineers call the acquisition phase, and it is a huge pointing problem. Yeah, this visual here pretty much says it all. Even with our amazing deep space network, there are still tiny errors, maybe a few kilometers, in knowing a spacecraft's exact location. But over millions of kilometers, that tiny little error just balloons into this massive uncertainty cone. It's a huge volume of space where your target might be. So traditionally, the solution was just brute force. You'd use a big, wide-field camera, kind of like a spotter scope on a telescope, to find the other spacecraft. But this has some major drawbacks. The camera generates a ton of heat, which is a huge no-no in the vacuum of space. That heat can warp sensitive instruments and force you to wait, delaying the start of the real science. So researchers came up with a smarter approach. What if, instead of a hot, bulky camera, we just used a really smart predictive algorithm? And this new solution is basically a smart steerer for the laser. It's built from 2 key components that work together just beautifully. So, the system has 2 main parts. First, you've got the muscle. That's the point-ahead angle mechanism, or PAM. It's the piece of precision hardware you see here that physically moves the laser. And then you have the brain. That's an algorithm called the Adaptive Extended Kalman Filter, or AEKF, which does all the heavy thinking and tells the PAM exactly where it needs to point.
So what on earth is this Kalman filter? Well, think of it as a super-powered predictive tool. It takes in messy, noisy data, in this case from the spacecraft's navigation sensors, and it uses a model of how the system is supposed to behave to spit out a clean, super-accurate estimate of what's really going on. It predicts, it measures, and then it corrects itself, getting smarter with every single step.
Okay, so let's break down how this brain actually thinks. The logic behind it is this really powerful loop of predicting and then refining that prediction. Think of it like you're trying to navigate in a bad storm. The filter starts with a really noisy, fuzzy GPS signal. That's the input. Then, using a map and your last known speed, it predicts where you should be in the next second. Finally, it gets another little ping from the GPS, compares it to the prediction, and refines its estimate. This cycle just keeps going, turning a fuzzy guess into a sharply filtered, incredibly precise location. And hey, don't just take my word for it. This is a quote straight from the researchers themselves. Their goal was crystal clear: replace the hot, complex camera with this smart algorithm. The result? A simpler, more efficient system that could get the science mission started way, way faster. So the theory is fantastic, but does it actually work? Well, the researchers ran a whole bunch of detailed simulations to find out, using super realistic models for all the sensor noise and orbital errors you'd expect. Whoa, okay, look at this. This graph shows the filter in action. That chaotic blue line bouncing all over the place, that's the noisy raw data coming from the sensors. The nice steady yellow line, that's the true correct angle.
And that beautiful purple line, just hugging the yellow one perfectly, that's the Kalman filter's output. It just cuts right through the noise to find the real signal. It literally turns chaos into clarity.
The results were, to put it lightly, pretty dramatic. When you compare the scan time of this new method to the old one, the improvement is just staggering. We are talking about a 99.5% reduction. That's not just a small improvement, that is a complete game changer.
And this chart really drives the point home. The old conventional method took, on average, over 1,600 seconds. That is almost half an hour. The new method, combining the PAM with the AFK brain, found the target in just 8.6 seconds. That's the difference between waiting for your coffee to brew and the blink of an eye. It's just incredible.
So, what's the bottom line here? The new method is better in every single way you can measure it. It's simpler because you're replacing clunky hardware with smart software. It's ridiculously faster, cutting that search time from minutes down to seconds. It's more robust, meaning it can handle big errors and still work. And it's way more efficient, letting scientists get to the real work, listening to the universe, sooner.
And that leaves us with a pretty fascinating thought. This technology was designed for detecting gravitational waves, but its implications are so much broader. I mean, when you can aim lasers this precisely over cosmic distances, what else does that unlock? What does it mean for high-speed data links with Mars, for autonomous navigation across the solar system, and for the entire next generation of deep space exploration? The possibilities are truly exciting.